Okay, question. What are the divisors of 30? What numbers divide evenly into 30? Can you list them without leaving any of them out? Now, there are two ways we could do this. We could start dividing 30 by 2, which works, and then by 3, which works. 4 doesn't go into 30. 5 goes into 30. 6 goes into 30. 7 doesn't. 8 doesn't. 9 doesn't. 10 does. 11 doesn't, and so forth. We could go one number at a time and test every possible number. If we have a very large number, that would get pretty tedious. However, if we know the prime factorization, we can list the divisors fairly easily. If 30 equals 2 times 3 times 5, then the divisors of 30 are as follows. Well, let's see. 2 divides 30, since 2 is one of the prime factors. 3 divides 30, and 5 divides 30. Now, of course, that is the first three numbers, or those are the first three numbers that we found, but there are more. Okay, what other numbers divide 30? Well, we got 6 and 10. And, yeah, okay. So how could we possibly get those numbers? Well, we could take 2 times 3, or 2 times 5, or 3 times 5. Three of these divisors have single factors. And I'll use P for prime. 2 prime factors. So we can just list every possible pair of prime factors. And, of course, 1 and 30 are also factors of 30, but I didn't list those. These are the non-trivial divisors. If we list all the divisors, we would also have to list 1 and 2 times 3 times 5, which, of course, is 30. So we get 6, 10, 15, and 30 itself. Now, what are the sum of the divisors of 30? And actually, I got a little bit of an error here when I wrote this down. I was a little careless. I want the sum of the proper divisors. Now, you remember the word proper from set theory. It meant that the set, a set is a proper subset if it's a subset of another set and not equal to the other set. We don't include a set among its proper subsets. And the same way we don't include a number among its proper divisors. So the proper divisors, the sum of the proper divisors is what? Well, we've got them listed here. 1, 2, 3, 5, 6, 10, 15. So if we add those, 1 plus 2 plus 3 plus 5 plus 6 plus 10 plus 15. What's that equal? Well, if we do the arithmetic, we got 25, 31, 36, 39, 40, 42. Okay? Now, we observe that the sum of the proper divisors of 30 is bigger than 30 itself. The number has divisors that add up to more than the number itself. Okay, well, we give a name to that. We say that we got a lot of divisors here. And the name we give to having enough divisors and also large enough divisors, and we have enough divisors and there are enough big ones, we say that that number is abundant. We have an abundant set of divisors because they add up to more than the number. 42 is bigger than the number that the divisors came from. Okay, now there's another alternative, of course. A number doesn't have to be abundant. there are some numbers that are deficient. Okay, I say 21 is deficient. Now what do you think I mean by deficient? If abundant means that the divisors add up to something bigger than the number, what does deficient mean? Well, this means that the divisors add up to less than the number. Now the divisors of 21, 21 equals 3 times 7. So the divisors are going to be 1, always, and 3, and 7, the two single factor divisors. And then, well, there's only one double factor divisor, which is 3 times 7, and 21, which is 21 itself. If we add up the proper divisors, we get 1 plus 3 is 4, and 7, we get 11. Now we note that 11 is less than 21. Yeah, it's less than 20 also. My hand doesn't seem to be connected to my words or to my brain. Okay, 11 is less than 21. So we say is deficient. 21 is deficient. Its divisors add up to less than the number itself. Most numbers are either abundant or deficient. Now what's the alternative to being either abundant or deficient? Well, the alternative to having abundant means the divisors add up to more, the proper divisors add up to more than the number. Deficient means they add up to less than the number. Is there any alternative to adding up to more than or adding up to less than the number? Well, yeah, the alternative is what we call perfect numbers, where the divisors add up to the number itself. And there's an interesting question that we'll just pose here. We're not going to actually try to answer that question, but is the number of perfect numbers infinite? Are there infinitely many perfect numbers? And we might first ask, are there any perfect numbers? And I'll say yes. One perfect number is 28. Okay, so there are some perfect numbers. And your book kind of gives this one away, so I'm not going to tell you anything that you were asked to find out for yourself. But 28 is 2 times 2 times 7, so that the divisors are 1, 2, 7. These are the 2 and 7 are the one factor divisors. And then we're going to have 2 times 2 or 2 times 7. Those are two factor divisors. Or, of course, 2 times 2 times 7. Put that in parentheses because that's not going to count among our proper divisors. Now, if we add those numbers up, 1 and 2 is 3, and 7 is 10, and 4 is 14, and 14 makes 28. So, 28 is a perfect number. A good exercise that I'll just suggest is write down all the numbers from 1 to about, say, 36, and see which ones are abundant, which ones are deficient, and which ones are perfect. If you do that, you'll discover another perfect number, at least one other perfect number, and you'll get a good idea how numbers become deficient or abundant, what it takes to make a number deficient or abundant.